Hi, Jenny. That's just good problem. So what's your theory about that one though? I thought because the memory is not 100%.
Good morning. I guess we're waiting for everybody else. Thanks for being on time.
Morning.
Hey, morning, Patricia.
How are you guys doing?
Good morning, Rashid.
Good. I have the slides ready to go. I'm just waiting for folks.
Okay. Yeah, so I didn't send an email because I've been traveling non-stop. So I'm done with traveling. But so I wanted to maybe hear from all of you, what did you think about the OCP, the Global Summit? I think most of you were there. Yeah, what do you guys think about the event, about the Chiplet movement? Like what
Actually, it was very good. I found it extremely good. Of course, there are too many interesting things simultaneously happening, so it was difficult to choose.
Yeah, it's
Yeah.
always an interesting event.
Yeah, there are many things happening. But there were one particular talk that I found interesting, and I think is very relevant for us. Um, so and there is like it's like different companies that are working together towards the chiplets, towards putting together an ecosystem for chiplets. So I think the speaker was Eddie Rodriguez, if I'm not wrong. So maybe we should reach out to them and see maybe if they can talk to us a little bit more about what they are doing and how we can maybe join forces with them as well to see.
What company was that? Sorry, Eddie, from which company?
I don't remember. I'm sorry. I remember his name, but I cannot remember exactly the company. I have his card. I just have to go and look for all the cards I
Okay.
have. But so yeah, so we can definitely reach out. And he's kind of the representative, but there are many companies in that group, in that working group. So yeah, we should definitely try to reach out to them. So we'll probably maybe do that during this week. The other thing that called my attention a lot, and I think it's something that is super relevant, is Arvind talk during the Thursday session. So I don't know, Arvind, if you would be willing to maybe share with us a little bit more of the work you guys are doing. I know in one of our meetings.
Yeah, I could do that.
Yeah, so I found that talk super interesting, and I really like the idea that you're saying, okay, we're gonna take edge computing as an example, but it doesn't, I mean, it's just an example to get going. And then it doesn't necessarily mean that it's not going to apply to other fields. So I think it's quite interesting. And then we also have a lot of edge computing, HPC edge computing in the lab. So definitely it's not necessarily something that is far away from what we're thinking about. So is it okay? Like, do you mind if do you want to maybe give a talk, or maybe we can have a discussion around your talk next time?
Next time would be 2 weeks or 1 week?
Yes. 2 weeks.
2 weeks. I'm just looking.
So it would be on November the 12th.
In principle, yes. Could I just confirm with you a little bit later? But I'll just check my calendar. In principle, yes, it should be okay.
Okay, yeah, I'll send you a reminder, and then if not, we can.
Sorry. I just realized I do have a client engagement on that week on the day. I'm not sure I can.
Oh, okay.
May have to do it the following one.
Okay.
The
Yeah, let's
following
find
one, by the way, is Thanksgiving week.
Uh,
We might want to skip that.
yeah, good point.
Okay, we can figure out a time.
Let's
But
figure out a time. I think, yeah, I'd be happy to do so.
Mhm,
At this moment, though, I just realized I do have a commitment on the 12th.
yeah.
I think
Let's figure out-
I also got the same out of Arvind's talk, as a very good talk, Arvind. And I think he also had almost like a call to action, essentially. Hey, can we get more help or something, more support? So that's like something
Yeah.
that triggered.
Jawad actually did approach me afterwards and was interested in making this an OCP activity. So I think maybe we can have some discussion about how to do that.
Right. Yeah. I mean, possibly here or possibly in some other work stream, but I think we should be definitely, I think, hearing
Okay.
more from you as to how we can all kind of approach this to problem solve after we understand exactly what you might be looking for.
Yep. Yeah. Okay. Thanks.
I think the
Um,
other thing on the same note, sorry, Patricia, I think, sorry if I cut you off, but I think the other thing along the same lines, I think I was thinking about even a good talk from the ANSYS CTO. Forget his name, I'll pull out, but they're also doing a lot of interesting things around HPC and maybe HPC profiling. I think ANSYS is a well-known company, as far as I know, doing a lot of stuff
Yes.
around HPC, right?
definitely.
So I think
ANSYS is going to become part of Synopsys.
Synopsys, which is also interesting because Synopsys is doing a lot of work around chiplets and chiplet EDA tools.
So Synopsys, yeah. So Synopsys has something called a platform architect, which is a chiplet modeling platform. I actually, at the Chiplet Summit in January, I spent a long time at their booth looking at the tool and all its capabilities. It looked pretty incredible. So that might be a good way to tack on.
Yeah, no, good, good, Arvind. I think I'm also thinking as we build up this forum and try to build up some momentum as to what we want to do, it might be good to kind of base level as to what the industry is doing already.
Mhm.
And I think what ANSYS is doing and what Synopsys is doing as to what Arvind is saying, maybe try to bring them in besides what Arvind is going to share with us, right? It'll be good to kind of baseline where the industry is.
Mhm.
And then we can build, okay, where are the other next set of gaps that we can go and tackle?
Right.
So Raghu and Arvind, would you guys mind then maybe dig out a contact that we can reach out to? Maybe to have a
In
conversation.
Synopsys or in ANSYS or either or both.
Either, both.
I don't have the personal contacts with ANSYS. I know people internally who do. Synopsys, I can probably help a little more with that if others don't have a name.
Yeah, I don't know. I know ANSYS. I mean, John Shelf was a panelist. I can approach both John and I forget what his name is. The ANSYS CTO, and I can just keep you all say, hey, sorry.
Was that the one who gave the talk? Preet,
Preet, thank you. Yeah,
Yeah,
Preet
he was
Banerjee.
really excellent. Yeah.
Yeah, he is very excellent. I think he also might have very good future looking. Where are all the gaps and where are things that needs to be solved, right? Oh, I
Right.
think Anshu is saying he can help with answers. So I guess he's
Okay.
on chat. Okay, can you assign the action? I don't know. I'm looking at George and Patricia. If you want to just assign the action to Anshu, he's
Okay,
going to
so,
bring
I
in
know a
the.
couple of people at ANSYS, Norman Chang, Preet, and there's another guy, John Lin, I think is his name. So I can reach out to them.
Okay, cool. Thank you, Anshu.
Let's do that. And yeah, let's do that. So I'll reach out to Eddie Rodriguez for that coalition that they already have going on. Then I'm sure you're gonna reach out to ANSYS. If you guys have someone in the tool that you guys were looking at in the OCP, in the Global Summit, you guys have someone for Synopsys that will also work. And then, any other contact that you guys think might be relevant would be good to maybe call them in. I don't know if people are scared of joining another work stream, but just, having an idea and talking to them to get information would be great. Okay, so if no one, is anyone has another topic to discuss?
I think we can move on. We have a lot to talk about.
Okay, so if no one has anything to discuss, so we talked with George, we had long discussions about where should we be going from now on. And basically what we have to keep in mind is that we want to develop a standard for creating a modular system. And we have to start thinking about how this standard is going to look like. And what are the things that we need to focus on at the different levels to generate this standard. So George condensed all these thoughts in a really nice slide set that so I think I'm gonna give it to George.
So, yes, there's a lot to talk about here. I think, as Patricia said, the question is, we've been talking about many things, so that's great. But how do we map our next actions? Because we want to keep the target in mind. We've been learning, talking about many great things, so that's great. But let's figure out a way to make progress. And I know we've been talking a lot about how many applications are the dominant, or which applications are the dominant. And that's obviously useful, but it's really hard to pick the top X most pressing application for HPC. I mean, first off, that changes, especially now with AI, that changes. Also, it changes by the system. I mean, we have experience with NERSC, but if we over-design based on what NERSC sees, like maybe Oak Ridge is not going to be interested. It's hard to, yeah, so we don't want to limit ourselves in that way. And of course, there's a data center world that has a different set of workloads. So we don't want to overfit for a specific workload that we just happen to have access to. So really what would be nice is to teach the community, if you have a workload, and we may not know what it is, but you do, is like, how can you get from there all the way down to integrating some specialized hardware for your system? The steps you see here are sort of some conceptual steps. Application is the workload. Profiling, I have some examples of that. I know we talked about a bit, but we also have some examples, as I promised you, at the end of this presentation. Then design specialized hardware. This is RTL and all the conventional hardware methods, some of which we talked about. Chiplet specs. A lot of what we want to produce in this workstream is the chiplet specs, and of course the how to actually integrate it. That chiplet specs includes also, I mean, the dimensions, but also protocols for communication and all that. So really, instead of like, we will hopefully be teaching the community how can they go from the left to the right of this flow using what we show them, and then produce specifications or standards that will help everybody have something to target, so that the system integrators have also something to target. So there's some common language between the developers and the system integrators. By the way, I have a bunch of slides, but you can stop me at any time for any
No,
questions.
first I agree with you, George. I think that I don't want to overfit and over-index on just Perlmutter, but Perlmutter was the best data set that we got. So I just said, let's start there, right? In terms of at least the first step, application and profiling. So, but
Right.
yeah, totally right. We don't want, I mean, if there are other good, similar examples from other HPC clusters that we can get, I think we should.
Yeah.
But
The other
yes.
problem with profiling, and that is true for, I think, all the HPC systems, that if we profile the system, is that even if we find that a certain application dominates, we don't necessarily have access to its code or its data. So we can't, so the system profiling that identifies like the piece of the pie that application is a system, but then there's the profiling within the application to figure out the kernels, and we need more access to the application to do that. So we were talking with Patricia is, okay, let's get this process started. Let's go from that left to right that I was talking about and pick 2 applications that we know are important. They might not be the top 1 or top 2, but we know they're important. They've been important for a long time. And we do have access to code for both of them because they're open source. I'll explain. I have some links coming up. So let's just pick applications that we know are important and they can serve as examples, or I mean useful examples, not dummy examples to complete this flow. One is density functional theory that comes from material science. I think we've talked about a bit. I have some more slides. And the other is a high energy physics problem. That's particle track reconstruction. I have more slides about that because it's more new. There's really a Kalman filter, and that is something that with Patricia we've been looking a lot into. Well, a lot with some for other projects too. It seems to be an interesting problem. And density functional theory is important for many applications. So it's, that's why it doesn't necessarily appear in the pie chart we show you for Perlmutter, because it's hidden within other applications, but it is important. So, without me being a domain scientist, I tried to put together some slides for those applications just to give you an idea of what those are. So for DFT, it's about predicting the material behavior. So a lot of that, those domain scientists use DFT as a kernel based on quantum mechanical considerations. So I mean, you can see it here is it's a grid. There's electrons, there are cores, other kind of particles, and it's trying to model the interactions between the two using some complicated physics. Let's just say that for now. And this is a peek about how complicated these physics are. There are a bunch of equations, and this is the computational loop. It's basically, it starts from an initial density, calculates these equations. It then, based on that result, calculates the new density, and then it checks is the new density that I calculated the input density. And I think that's something about the nature of the problem. If yes, done. If not, but it does loop many times. What is interesting, what stands out about DFT, I guess there's a typo in the title, DFT, is that it's a lot of, it's very math heavy. And part of the goal of this profiling, when we figure out here, what's the ratio of compute versus data? Because equations can be compute heavy, or they can fetch, or they can be compute bound or memory bound, is what I'm trying to say, depending on how big of data set each iteration brings versus how complicated the computation is. And here we see there's a lot of, like, there's in the integration, there's some, so this gives the impression that it's compute heavy, but this is one goal of the profiling. We need to understand, like, if this is computer memory bound, and also what kind of like data sizes is realistic for DFT. Also, do they need floating point or not? That kind of thing. So there are questions about DFT, but this is a quick intro. Now, the high energy physics, this is the coolest figure I could find about it. And it is the core of Atlas. And Atlas, if you remember the pie chart, is 25%, 26% in Perlmutter. So it is a big part of Perlmutter's workload. And I forget right now, it was 26% in CPUs or GPUs. It was one of the two. It wasn't 26% on both. But anyway, so we have this particle detector, it has slices, and then there are particles going through it. And each slice captures a snapshot. So at certain points in time, it takes a picture, and little dots that appear by every slice means that there's a particle here. And the goal is to reconstruct all these little lines that you see. Basically, how did particles move through the detector? It's a really cool problem. Now, computationally, what that means is that the image that we're dealing with, as you can see here, there's a simple example with these black dots, and these black dots are hits from one particle. This is a simple figure from a tutorial that basically shows only one particle, just to show the problem. And the goal of this is to find the track of this particle. So it starts with the seeding, and I'll show that again later, which is basically 3 hits in sequence. And based on this 3 hits in sequence, that in this case starts from the center. Like, so, by the way, here we're looking at the detector like top down, like we're sort of looking inside the tube. So from the seeding, yeah, and every ring is one of the slices that I showed you before. So from the seeding and all these other hits, we want to get this blue line. We want to reconstruct that this is the track that this particle followed, and Kalman filter just gives a little, like it narrows down the area to make that possible. So basically track finding is these dotted lines, and the fitting and classification, which is like a step after the Kalman filter. Although as I understand it, the Kalman filter is the intense part, the computation intense part. Yeah, so that blue line is what we're looking for. Now, it's simple here, but if you have a realistic picture, it looks like this. So here we see a snapshot from every one of those slices in the detector, again, looking top down, and we see a whole bunch of particles. And the goal is to find out the track, right? And this shows why it's a hard problem, right? There's so many particles. So it's a really computational intensive problem, which is a good thing, because that's what we're looking for accelerators. It's also a problem that 26% in Perlmutter, so it's an important problem.
That is CPU, by the way. I was looking at your pie chart.
Oh, okay, it's
Perlmutter,
CPU,
26% on Atlas is 26% on CPU only nodes, also 3.5% on GPU accelerated nodes. So I don't know, sounds like at least the research community is not seeing much of GPU-centric computing out here, but
I suspect that will change because there is an implementation by CERN about this. Actually, it's the link that I have here, and they have CUDA versions as well. I don't know why people don't use them. Maybe there's a good reason, but the point is they're looking into it, because this problem appears to have good parallelism. So I would expect people to want to use GPUs. Maybe they haven't done it yet, but in any case, okay, thank you. 26% on the CPU side, and I know it's an important problem because, like, the is it the no, is it the BES, I guess, Office of DOE's recently had a call about this. It probably will have more calls. So it's an important problem. So in this complex snapshot, again, not a domain scientist, but I'm going to try to reiterate what I think I understood from a tutorial here. Is so they take all these many snapshots, and the first step of the algorithm is to form these seeds, and seeds are 3 particle hits that they try to group together, in the sense that those 3 hits are probably the same particle. And yeah, so so triplets of spacing points, and there are details about which subdetectors and so on. We don't have to go through that now, but basically we start with these triplets, and then they try to extend these triplets with these green marks, I guess, trying to find, like, yeah, the hit that's next to this seed, this triplet, is likely the next particle. So basically try to make the triplet into what would be the word, quadruplet or something, 4 points. And so that will form a new seed, and then they form roads, what the tutorial at least called roads. These are basically parts of the detector modules that are expected to contain clusters compatible with the seed. So basically, these are the hits that we should be considering to attach to the seed. That's sort of what this means. It's like they're finding other hits that are probably also the same particle. Now you can see that in some cases, these red areas, yeah, they look straight, so they kind of make sense. But other times, these red areas are a little less successful, so they form these that, I mean, intuitively at least, it looks like some of these are probably the same particle, but not all of them. So, but anyway, that's the next step of the algorithm. And then here's becomes a little more complicated. And then these seeds are extended using the Kalman filter, using the combinatorial Kalman filter, which basically it searches these adjacent clusters up and down, inward and outward is what they call it, and it attempts to smooth the trajectory. I'm not an expert enough to understand like how all the details here, but basically this is the step where the Kalman filter applies. And then anyway, and then there's another step that extends that to a large area, checking for even more compatible hits. That's what they call the region of interest. And the final step is the tracks. So this is like a graphical representation, but the computational loop is sort of like this. It goes from basically these steps that we talked about it's really nothing new. But what the tutorial was mentioning, and I've talked to people and they said the same thing, the Kalman filter is the computationally intensive kernel here. So even if we just focus on that, that's perfectly fine. If we want to build an accelerator for a Kalman filter, that's the difficult thing here. So both of these benchmarks that I talked about, they're available to download. So this HPC problem that I just talked about is, there are more than one implementation, but the simplest yet realistic one that I found comes from CERN. It's called Track with 3 C's. And you can find the link here. It has multi-threaded, single-threaded, and CUDA version, so you can run it on a GPU. Now, again, I don't know why people don't need Perlmutter yet. Maybe the implementation is not good. I don't know, but I suspect they will sooner or later. And density functional theory, I mean, there are many out there, but here's one that I found that seems to be more minimalistic and therefore easy to understand and run. We're going to upload those slides later to our site. You don't have to write down the URLs. So these are good starting points, is the point. Like, we don't have to look at all the applications Perlmutter runs. We talked about at the beginning here. These are 2 good applications that we sort of understand and we have access to and we know are important. So we can just start from them. Now, I promised you an example for profiling. Say that we have the code. Stuff, like I said before.
Hey, one question I have, George.
Yes,
Sorry.
yes.
So by the way, it's very good. I also am aligned to get like 2, start with 2, 1 or 2, right? I think 2 good ones that you think are like very, very computation intensive, right? We can make a difference. One question is this, and I can also do some reading offline. By any chance, and I also have a paper on high energy physics that I can also like read through again and maybe come back next time. But I think the question is there any connection to this to quantum physics or quantum mechanics? Like a lot of quantum computing is happening.
Not computing, but my understanding that is that DFT also has some quantum mechanics modeled, but not computing. There's no quantum computing here, if that's what you mean. Yeah.
Okay. No, I'm saying some of the kind of the principles that you shared. I'm wondering if it can also be applied to some of the quantum computing.
I don't see a connection, but I'm not expert enough to know
that's
that
fine.
for sure. Yeah.
Okay, that's okay. I'm just trying to see what is the next big problem in the industry. And
Yeah,
definitely
I would think quantum computing kind of abstracts this out.
Okay. Okay, possible. Again, I said my intention was to see if there's any, if this is like kind of connected to some large problem the industry is looking at, so we will get more traction. Okay, all right.
Okay.
Thank you.
Okay, very good. Okay, so an example of profiling, and there are many ways to do profiling. There are many packages out there. I'm just going to show you one, and particularly the one I'm going to show you is based on AMD's tool. Intel has an equivalent tool. There are also open source tools out there, like Tau, I think, is one that people talk about. Cray has one as well that I've used before. It has its pros and cons, but the one by AMD is just, I installed it in Perlmutter. It has AMD CPU, so it sort of made sense. So here the question is, assume we have the application code. Now we want to find out, okay, what is memory bandwidth, what's computation, are there stalls in the CPU, and like stuff like what we just talked about earlier. I'm looking at an equation. Is it memory or compute bound for a specific set of input data? So AMD and Intel CPUs, I'm going to focus on AMD, but it's the same thing. They have a lot of hardware counters available, even for non-root usage. And you can also use perf, by the way. That's also a little, I think that's more command line, but that's also very usable to gain access to them. But all those are collectible through all these profiles. So I'm showing you examples of how I run this AMD tool. You don't have to remember it. This is just to show you as an example if you want to play around offline. It's basically you invoke the profiler, you tell it what to collect. In this case, like the timing and IBS op, this is a profile you can find it needs documentation to do. Basically, it says collect compute information from the cores. There's others like MPI, profiling, and so on. And this is the output that it stores the spreadsheet that it's going to give you actually it's well, no, it gives you a whole output directory with data files. This is the application and the user application in this case and the data files. And the last step is based on the output directory, generate the report. So in concept, it's very simple, like the Cray compiler and others follow the same thing. There's a profiling step, and then there's a processing step. Some profilers, like the Cray one, have like 2 modes of profiling, and if you want the more detailed one, you have to link some libraries from the profiler when you compile the application. And that can make it powerful. It can give you a lot of things, but for some applications that use complicated build structures, it can be a headache. But for this profiling that I did here, I didn't need to do that. It's basically you invoke the profiler that it sort of contains the application. It then invokes the application. So one of the things you can get are, yes.
Hey, George, I have a question here. The use of this profiler, they are running on hardware or benchmark softwares.
So
are you running this on hardware, like GPU?
Yeah. This is running on native hardware. I mean, I run this on Perlmutter. You can also, you can also run this on GPU, but you have to use NVIDIA's tool, well, depending on what GPU you have.
Yeah, so actually my end question was like a profiler give you the data, a lot of input, I mean, statistics, right?
It will generate a lot of statistics, if that's what you mean. Yeah.
Yeah. So are you going to use that for tuning your software stack, or because GPU is already designed and in the system, right? You cannot make any changes.
Correct.
Is that the correct understanding?
Yeah, you're not going to change the hardware. Yes, that's fixed. You're trying to understand the application. You're trying to understand, like, for example, the byte per flop ratio. How many bytes of memory access per floating point operation? You're trying to understand if your application is more computer memory bound, if it stalls a lot, if the caches work well for it, that kind of thing. You're trying to understand the behavior of the application, and you can change the application later. But in this case, like usually we do, we profile on real hardware, and therefore we cannot change the hardware. Now, you can also run your application on something like Gen 5, which is like a simulator. And in that case, you can change the simulated hardware, and that's a different thing, but I'm not doing that here.
Okay, thank you.
Yeah. But yeah, good question. I did not clarify that. So, okay, so what can the AIM do to give you? And it's obviously a lot of things. I'm going to give you just some highlights here. One of the things that they give you readily, they have a script ready for that, is this roofline analysis. So what this line and this dots up at the top are basically the maximum specifications of the hardware. You have arithmetic intensity, so flop per byte of the application on the x-axis, and you have throughput of the computation, so in gigaflops on the y-axis. Anything below this line and to the right is what the hardware can do. And in fact, the peaks are here. They just highlight the peaks for whatever. This is single point, floating point. This is single precision, rather, floating point, double precision, floating point. And you can see you can do, like, in double precision, 5,000 and change gigaflops. The application that we just run is this dot here. In this case, it's a multi-threaded version of the track HPC benchmark with some test data that they give you. So, for example, it shows you that you had 8.45 gigaflops. This is your memory bandwidth. This is your flop per byte. So it measures the application, it runs it, and it just plots it. Now, of course, just looking at this, it shows, oh, well, I'm actually not using the hardware very well. I'm not near this line. I mean, we want to be somewhere close to this line, that these are the limits. And of course, there are many reasons why the application cannot be at this line. Oftentimes, and what this graph is trying to highlight, is the memory bandwidth. That's what is not. So if this line were to move up, it means that it is more compute intensive. And memory bandwidth is one of the reasons, oftentimes, that it's not able to go up, because it's just waiting for data. So this is a quick way to visualize that. So from this, it tells us that this benchmark appears to be memory bound, at least to a large degree. This is throughout its computation. It doesn't mean it's memory bound all the time. Maybe it goes through phases, but at least by average, this is what it looks like. So this is the roofline analysis. Now it has a GUI that gives you many things that I'm not going to go through all at one, but I'm going to give you highlights. One of the things it gives you, remember, we had this question, where does an application spend most of its time in? And this is a breakdown that will give you that. Now, of course, it's, function names can be complicated after compilation, depending on how the program was written and all that. But these are function names, and it tells you what module, basically what file code it was. And this is the time in spend, and I forget like what the maximum is. Yeah, okay, so it's like, for some reasons, 4,800% is the total, but basically a quarter of the time approximately is spent in this function here. And then the other functions are way less. So this right here tells us, let's find this function, because that appears to be the intensive part. Whether it's waiting for data or compute, we don't know. We have to look at the function, but a lot of time is spent here. And there are others, and this is more like, yeah, okay. So here you get a collection of hardware counters, and there are many to choose from. I just left the default here as examples, and okay, maybe these are not the hardware counters. This is just profiling statistics. Anyway, I think you could put hardware counts here as well. But basically, it tells you by function a bunch of statistics, whether that's hardware counters or other kind of statistics. So, for example, these are the load operations. These are load or store operations. These are stores. Basically, tells you how many memory load or store operations you had, and this is all the ops. I think, yes, these are all the ops. So I think that includes loads and stores. So it tells you that most of this function is loads or stores, for example. So that function is doing a lot of loading. But if you look at, I don't know, the third line, now only less than half of the functions of the operations are loads and stores. So focusing on, I mean, we configure these columns to answer a specific question. Here, the question is, okay, what's the ratio between memory operations and other kind of operations by function? And this is what this table is answering. And we can configure this table to have like cache misses or stall cycles. There's a lot, but this is statistics by, okay, that's all I have. Yeah, this is statistics by function. Now you can also get statistics, and I don't really show that here. Well, I guess I can do. You can also get statistics by time. So that's graph at the top is basically a time diagram of a specific metric that I guess the photo could cut off. But this is IBS load operations, I think. So basically it shows how the number of load operations varies by time, either by function or throughout the program. So you can get a little bit of an understanding of how spread out all these load and stores are. And you can get a lot more. And before I move on, any thoughts or questions?
I think other couple of, this is very good, George. I think the roofline analysis fix where you can start, right? Big picture, you
Yeah.
can get it. And then I think other couple of other tools I've seen is something called, I mean, we can think about it if we need it or not. There's something called flame graph.
I haven't heard of that. Okay.
Yeah, and other one is called top-down analysis. That is just gives you this almost, it gives like kind of the data flow from fetch, execute, decode to retire of the CPU flow.
Okay.
So it's top-down analysis. So when we get there, we can debate or check to see if that could also give more visibility into where the bottlenecks are.
Okay.
Going back to the roofline analysis, go back to that one slide. I mean, the only question I have is that, so I think it looks like it's in this particular situation, even if the green dot moves all the way to the top, essentially is picking up in the roof somewhere there, right? So that's what AMD EPIC is kind of flatlining.
Yeah.
And I
Yeah.
think
Exactly.
as we're doing that high energy physics example or other example, we can say, okay, what if we can move the roofline even up and to the right? right?
Exactly.
It could be both. It could be both objectives, right? One, can I move the roof line to up and above, up and around, and then second is also your dot, green dot, can also be moved as close to the roof line as possible.
If we design an accelerator in this, it's going to move both of these things. Yes,
Good. Okay.
exactly.
Correct.
But it might not necessarily change the flop per byte because that's a characteristic of the algorithm. Flops per byte is how many operations I do for every byte that I bring from memory, and that is part of the algorithm.
Correct. Right. Correct.
But yeah,
the flops per byte is basically set by the algorithm, but then how many flops you can do?
exactly. That's the y-axis, and that also moves up. Yes.
Yeah. Correct.
Yeah.
Correct. Now, I mean, I don't know. The only other thing I agree with what you're saying, but maybe the precision of the math can also make a difference, right? Because you're like, as you said, I think you're already showing dual precision and single precision, right?
If you break it out in kernels, it might be more illuminating here.
Yeah,
we can do that. What was I
it'll be
saying?
interesting to see if high energy physics can even benefit. It's more of a question, right?
And that's
precision beyond dual precision, essentially. Because
right
now
exactly.
we're bound by dual precision only because CPUs offer dual precision, but maybe that's just a constraint that is in the industry today.
Stuff to figure out, but if we design accelerator, these lines will definitely move up. Whether our dot, our application moves, is also a function of how constrained by bandwidth, by memory bandwidth it is. So
correct, and we need to solve for all of that. Correct.
Yeah, and it's not obvious, but we would like it to move up as well. Even if there's still a gap, we still want it to move up. All right, and then some systems like NERSC also give you some crude statistics about the job after the job is run. So this sort of uses the same mechanisms that we used to collect statistics a while back, which, by the way, we've put on hold now because the collection mechanism is still under development. They're changing some things, so right now there are no statistics being collected. But they also have a user interface for when it works that gives you, for example, the IPC throughout your job per node. I mean, again, they're kind of crude, but it still gives you an understanding. Like, hey, IPC is an interesting metric, or memory use. That's capacity, not bandwidth, or power. But it doesn't work right now. So, if everybody sort of is on board with going down this path, this is a list of tasks that will help through this path. So some of the stuff we talked about, some not, and this is where we could use your help. So we can start from understanding. So we pick two applications that are important that we have access to. Maybe there are more. So that is one task right there. If we can find applications that we know are important and we have access to their code, that'll be useful. And finding that application doesn't necessarily mean HPC. It can also be an AI workload or data center inspired. And the next step for that is to profile it. So either that new application or the ones we have, let's profile it, extract the kernels out of it. I sort of did that here. Where is it? But it needs more work to be kernels. Like we need to go into the code and figure out, like, is this actually a kernel? Is this sort of a library call? Is something, what are these functions? And sort of group these into kernels. And I think this profiler, like supports annotation, so you can make this breakdown a little nicer. But anyway, I didn't do that here. The third is decide metrics that are important for hardware design. So this goes back to, if we want to accelerate an application, what makes an application a good candidate for acceleration? We talked about flop per byte, and I have a sense that that's going to be a good metric or a good predictor. But maybe there are more, or maybe this is not a good metric. So we can discuss some candidate metrics that are important for an application to be to be a good candidate. The fourth step is more of a heavy lift, but design specialized hardware for this application kernels. Not the whole application, but for example, for HPC, there will be the Kalman filter. And there might be already something out there. I didn't look hard. I didn't find anything quickly, but there might be an implementation out there. And of course, it has to be, a scale that is interesting to the applications that we talked about here. And then based on that RTL and this implementation of the accelerator, now we have to estimate, okay, if we put this on a chiplet, how big is it going to be? What's the power consumption and density? And then how much bandwidth it needs to communicate with the outside world, and can we support that through the shore? And then based on so that's going to be our demands. And then the next step is, does the current technology, remember what Patricia presented a few meetings ago, does the current technology support those demands? Can we cool this chiplet? Do we have that bandwidth density? Do we have the protocols to support it? I mean, we probably do. But anyway, let's make a list. Are there any gaps? Can we implement this chiplet today is basically the question. And then the last step is, now let's look at the system, or we can just focus on one rack. Let's assume that I have a chiplet here. How do I tell the job scheduler to use that chiplet? How do I make sure that the job scheduler puts the data of that application close to the chiplet, maybe hopefully on the same node, maybe on another chiplet that's next to our computational chiplet? Because we've been talking about compute chiplets, but memory chiplets are also part of this. So this is more of a researchy topic because it can be broad, but it's also important because the chiplets have to be usable. So I think that's all I have. Yeah, that's all I have. But this is a list of tasks, inspired by what we're talking about. If you guys are on board, it'd be great if we can get help, because cannot do this all alone. And that's all I have.
No, I think thankfully I've been reading about high energy physics, George. So I have I was just really looking into that right now. I was pulling it up. And that is the cloud side of it. And there is actually a paper from CERN who are using, I think, some concepts like software called Root. I don't know if you know, ROOT.
I don't know that.
And
no.
also another software called R Data Frame that is managing. So I know, so I'm seeing this from the top down. There are some cloud tools and software tools that are being used for high energy physics, and they have been published. They published it in the Journal of Supercomputing.
Mm.
So at least I can kind of read that one more time and see how it kind of connects to what you have shown.
Okay, that would definitely help. I mean, if you can, okay, yeah, that will be a good action item. And then the next step is see if you can find, because implementing it is difficult, if you can find some sort of specialized hardware for this out there. Maybe there's something out there that we can use, like a Kalman filter, or maybe we can ask people, contacts we may have. If we can get our hands on an RTL for this, even if it's not fully sophisticated, but some sort of RTL, then we can make progress on like identifying the properties of a chiplet that would host this RTL. We can make progress for the rest of the steps. But the most labor-intensive part of this flow is designing the RTL, I think.
When you say RTL, are you saying what? What does RTL stand for?
It's basically a hardware, like Verilog or Chisel.
Okay.
Registered transfer level.
No,
Yeah.
I kind of suspected that was the case, but
It's
I'm wondering
synchronous
if that.
finite state machine, really. So there's a difference between synchronous finite state machine and asynchronous, and neural networks for AI is more asynchronous finite state machine.
Basically a hardware implementation. Yeah.
Okay, no, that's what
all.
I suspected, because I was wondering RTL. I'm wondering if we may be a little bit too early for that. Is it possible to get the roofline analysis for Atlas, or at least for the job?
Atlas is
or
a
job
really
that is the high energy particle physics, right?
Atlas is a really complicated set of tools and suites, and I tried installing a related application, but it was too hard, and I couldn't even find data for it, realistic data. That's why I settled into this track from CERN, because it's considered to be realistic and yet doesn't have all these unnecessary bells and whistles. So we can focus on the kernel, the Kalman filter, on this one. So I think as far as the code goes for HPC, we're covered by track. If we can get the RTL for the, I think for density functional theory, we have RTL from our other projects. So RTL is covered here. It's just that we're missing RTL for HPC, for a Kalman filter, basically. And by the way, I'm not monitoring the chat because I'm screen sharing. Somebody can, I know if Patricia, you're looking at the chat, if there are questions here or something.
I threw in
yeah.
some links in the chat. One of the applications that I'm interested in is Zeiss, which is from Sandia Labs, which is a parallel processing circuit simulator. So if you're doing chiplets, you want to simulate the chiplets. So you want the circuit simulators to work.
Okay, so that's a good point because I did not talk about what tools we're going to use to evaluate the RTL and simulate that. That is one way to do it for sure.
Yeah, RTL is like the worst level to design anything at. The only reason we do that is because for legacy reasons that it was created in 1990 odd or something, and people have just like built this entire flow around
Okay.
RTL, but it's like the worst
Right.
possible level to work at.
Okay, that's a long discussion. Absolutely. Whatever tools
Get
or
started in data analytics. You don't need previous experience.
Sorry.
yeah, whatever hardware implementation works for you, whatever tools, absolutely yes. We can work with everything. We have RTL experience. We use Chisel. We have a set of tools in
I
the
would
lab, but
avoid
not
Chisel
Cadence.
and RTL if you can possibly avoid it. It's one of the
Okay.
things I put in there is the hotwrite.com link, which is for putting C code directly on FPGAs with
Okay.
microcode engines. That one's something Steve Castleman's trying to develop.
Okay.
And then this overlaps with what Alan Cantel's trying to do in the HPC meetup, which was just before this. So
Okay, great.
he's trying to build FPGA kind of platforms.
If that works, that's fine. I mean, let's not constrain ourselves to specific tools right now because it's hard. Like people work with different things, but I hear you.
Yeah, I mean, there's a general methodology that I was looking at for doing a lot of this stuff, whereas you just try and break everything into containers in a network
Okay.
space, and then you look at your container and say what's in here and what's going to run it well.
Oh, okay. Okay, so that's interesting. Is that something you can present to us at a future meeting?
And yeah, I can talk about it. Basically, there's an equivalence between a routine call and a message pass. So any routine you call can be looked at as a message pass between two computing contexts. So
Okay.
you can take code which is linked together and just say this is a big graph of computing elements which are doing message passing. That's one way to look at your program when you link it together. And then you can say, okay, how do I drop these pieces into containers efficiently? So you look at things like, which things are actually sharing memory, and then you drop them in a container together.
I would be interested in finding out more about this, if people might want to use something like this. But I mean, we don't have to use this, but we could, and I would want to know more about this. If you can spend a few minutes at a future meeting, that'd be great.
Yeah, there's things like if you know gzip.
Sure.
So gzip is something where somebody actually built a chip for running that algorithm. So there's a question of like, okay, I've got a chip that does gzip. How do I use it? So
interesting.
Okay. Like saying, okay, I've got a library which is a hardware accelerator. So when I'm linking my code together, I want to use the hardware accelerator.
Okay.
If it's there. So there's a lot of things where you actually want to push stuff into the linker in the runtime, but nobody does that.
Interesting.
Okay. So you can do.
Okay. Thank you for that. That's really interesting. Let's go into more detail at the future meeting. But yeah, so going back to this, in terms of the list of tasks, please, if it's something you can help with. So Raghu, thank you. You're gonna look into HPC, if I understand right, and you and I, and also others can look for some sort of implementation or a way to generate it. We're gonna talk about it in 2 weeks for a Kalman filter, and whoever wants to help with any of these would be great. I mean, I think for now we're mostly looking at the top of this list because the bottom depends on having like a hardware model.
So there is one thing that kind of worries me a little bit about this, and is the like here we have design specialized hardware for an application or kernel, and that's not an easy task to do. Like
yeah, that's what I said earlier. So that's
no, I understand that. So I guess my point is my point is, for example, let me give you an example. So we're gonna do all these, and let's say, so we do have the code, that we can run and we can experiment with for a 3-dimensional FFT, for a 3-dimensional fast Fourier transform, and that is well known. So I guess my point is, once we have this, how is this going to be translated into a standard for chiplets? So I guess my point is yeah. So that's exactly my point. Like, how is this going to translate into a standard? Because all this is a lot of work that, I mean, it can take a team and a lot of time to do.
So the hardware, if we can get I mean, we have already hardware for DFT, and again, in 2 weeks, we can find out ways to get hardware more easily. That will give us the demands of, like, if we are to run DFT on a chiplet, what will that chiplet look like? Size, dimension, power, and standards usually come from a consensus of, like, what is going to serve the majority of cases, right? And as well as what the technology supports. So you were looking into what this technology supports earlier at an earlier presentation. I think what we're missing is what would be useful to accelerate our applications, like not too small, not too big. We need that, like a ballpark.
Yeah, but how, like, how are we gonna do? Like, let's say, like, let's skip the step. You don't have numbers, but let's skip step number 1, 2, 3, and 4, right? Let's assume we have all that. Let's say next week I come up and I say, okay, I have a 3-dimensional FFT. I have hardware that runs, because we do have that. And then we know, like, we can profile an FFT very easy if it is not already there out in literature.
Sure.
Those numbers, what can we do? You know, like, what I'm saying is that we can have those numbers by next meeting if we want for a 3-dimensional FFT. Then now, how do we proceed from that point on, you know? Like, I guess my worry is that we're going to spend a lot of time looking into different kernels, profiling, creating, like, attempting to create hardware. And then what do we do with that?
So that's this bullet here, I guess is number 5. So if you have the specialized hardware and you want to put in a chiplet, what are the properties the chiplet needs to have to support this hardware? This is how big the chiplet is going to be. So basically, that's the size of the circuit. What's the density, the bandwidth rather, that it needs to communicate with the outside wall? How much power it's going to consume that goes into cooling, and reliability. I don't know. That maybe we can leave that for later. But basically, if you have a piece of hardware, if I want to put it in a chiplet, what specs must that chiplet have?
Yeah, and my question is, how do we get those specs?
So the size, it comes from the circuit size. The power is like a power density analysis and how much power is going to draw on, and there are tools, not free tools, I think, that do this. And the bandwidth comes from how much memory traffic it's going to create. So that comes from its computation intensity as well as its clock
Yeah,
cycle.
but I understand that, but, like, you know, like a Kalman filter that you were discussing now for HPE, and if a 3-dimensional FFT, those are very specific accelerators,
Right.
and they're going to have very specific metrics.
Right.
Then how is this going to, like, how is this going to translate into a standard?
So there are two
And
things.
that's not a question for you. I mean, I guess that's a question for the whole group, but yeah.
So, I mean, if we close this flow, that's also like we're teaching the community how to do this analysis by this. So that's one deliverable. In terms of the actual standards, again, standards are usually formulated by consensus, like what serves the needs of what we're trying to do. So we need some data points for this. And it doesn't mean that the data points are only ours. We can look at what others are doing. But since we are looking into HPC applications, we have to get some data points that serve HPC.
No, I understand that. So I guess the standard is going to be, okay, so we have a set of hardware, specialized hardware, and this specialized hardware is going to have these specs. Let's say that we can come up with three different one.
Okay.
So these three things is, like, how is that going to get to a consensus is my question. I mean, but not, I mean, not for you again, like for the whole group. Yeah, like, I don't mean to.
We have to start with one. I think George. I think George has at least got. We started one. I think, and actually, when you say chiplet, going back to that 5th bullet out there, I think when you say chiplet, it's not like one chiplet, right? Because you need to figure out how do you make this all modular, right? So it could be what are the 3 to 5 chiplets you may need, right? One memory chiplet, one memory, I don't know, one kind of compute chiplet, maybe a couple of other chiplets, IO chiplets we may need, right? And then, okay, now we have solved, again, this is all like, I still look at as paper analysis, right? So estimate the, I think, key properties of chiplet that would fit, and how many can fit on a package. Let's say the package's sizes are doubling and tripling. How many of these chiplets you can fit on a package that can increase the roof line higher and move the dot up, right? How would I bring these chiplets together in a way, if his memory kind of limited, can I add more memory fetches, right? In the chiplet, sorry, in the whole chip. If it's like compute constraint, can I put in more compute units, right? So at least we have to do the paper analysis first. And then if you can solve for one, then we can, as I think George is saying, then we can try to see, okay, what's the next one, or at least show the flow of how this was done. So I think we are to start with one.
I think we've been thinking a little bit about this, and at least our approach, I do have to run, but I mean, we've been also thinking of maybe a more generalized architectural simulator where you could put these chiplets in, put the effective bandwidths between them, and have it start giving you, performance estimations. So maybe that would be the step after a paper study. I apologize, I do have to drop.
Yeah,
I
same
think
here.
let's do a paper study first, and then I think I said Ansys may have some tools, right? Synopsys may have some tools, so we may need to see if those tools can at least give us a kind of a order of magnitude kind of direction on this.
Okay, so I'm gonna say, well, everyone has to leave now, so let's continue the discussion next time. But yeah, it's pretty cool. Thank you so much, George, for putting all this in paper so we can actually take a look at.
Thank you.
Okay, thanks everybody. See you in 2 weeks.
Thank you.